In the traditional tech industry, high-velocity software development usually runs into a massive, frustrating hard stop, the final security audit. Building an entire application and only checking for flaws right before deployment creates friction between teams and ensures vulnerabilities are discovered when they are the most expensive to fix. Solving this requires a structural reorganization of the pipeline. Security moves from being an isolated check at the end of the line to a core component of the development cycle itself. This relies on shifting left, embedding automated security checks directly into earlier stages of development. To see how this works, we will map the tools, controls, and methodologies required at each of the 7 stages of the software lifecycle. Distributing these checks across the architecture allows for high-velocity deployment while upholding enterprise-grade safety. The map starts at the plan stage, before a single line of code is written. Applying structural constraints early is significantly cheaper than attempting to patch compiled software later on. This data flow diagram maps user input moving to a database. Applying the STRIDE framework, architects overlay threat categories directly onto interaction points. Flags then trigger simulated threat vectors, prompting teams to use a 4-question frame to identify and defend against these structural risks. The answers to those questions dictate the explicit security requirements the engineering team must execute during the build. Threat modeling shifts security ownership to the developers, turning defense into a foundational architectural constraint. Following the pipeline map, the logic moves into the code and build stages. Here, developers use static application security testing, or SAST, which analyzes source code for vulnerabilities in real time within the code editor. Simultaneously, software composition analysis tools scan external dependencies and open-source libraries for known vulnerabilities and license compliance. The primary constraint enforced during these stages is OWASP Proactive Control 5, Validate All Inputs. While a deny list is easily bypassed by mixed-case tags, allow listing uses strict regular expressions to reject anything not matching a known good pattern. But syntax validation alone cannot prevent logic flaws that manipulate the underlying application state. Mass assignment allows users to modify restricted server-side objects. Attackers exploit insecure binding by injecting a rogue request for elevated permissions. The solution? Data transfer objects. A rigid DTO template placed before the API ensures payloads with unexpected data are physically sheared off. This constraint acts as an automated gatekeeper embedded directly inside the codebase. Enforcing strict input validation and static analysis at the code level eliminates entire classes of vulnerabilities before the software ever compiles. At the test stage, the process moves from code review to active behavioral analysis on a compiled environment. Dynamic application security testing evaluates the running application from the outside in, simulating real-world attack scenarios without needing the source code. To force unexpected memory leaks or logic crashes, tools known as fuzzers bombard the application with malformed, erratic data streams. Dynamic testing proves that the application's theoretical static defenses actually hold up under active hostile conditions. The final 3 stages of the pipeline are deploy, operate, and monitor. Because modern infrastructure is defined as code, it must be subjected to the same rigorous scanning as the application logic. Here, an infrastructure as code scanner parses a deployment manifest. It highlights individual lines of configuration and validates them against predefined security rules. This pre-deployment check ensures that misconfigured or exposed clusters never spin up in the first place. Utilizing GitOps principles establishes the repository as the single immutable source of truth for both application state and infrastructure security policy. Security requirements continue even after the application goes live. Cloud security posture management tools constantly scan active environments to detect configuration drift. Meanwhile, container runtime security tools such as eBPF sidecars continuously monitor live pods to detect any anomalous system calls. Extending continuous monitoring into the deployment and runtime environments creates a closed-loop system where drift and active breaches are caught instantly. Looking at the completed 7-stage pipeline, the landscape of isolated security tools resolves into a coherent, automated system. To manage this complexity at an enterprise scale, a unified framework called Policy as Code binds every node under a single governance rule set. Policy as Code standardizes security controls, ensuring consistency and preventing manual bypasses across all environments. The result is a defense-in-depth architecture, validating inputs at the code level, scanning infrastructure at the deployment level, and monitoring at runtime. This integrated high-velocity machine replaces the bottlenecked late-stage audits of traditional development. These tools are strictly enforcement mechanisms. True DevSecOps relies on the cultural discipline of shared responsibility among all engineers. Shifting left is the core engineering discipline required to build resilient software at scale without sacrificing velocity.